So, normal distribution, probably the most important probability distribution that we actually work with, is used all over the place. And because it can approximate a binomial and a Poisson quite effectively, it can be used in those kind of cases as well. So what you'll remember from a few lessons ago was that I split the board down into discrete and continuous. And so we've met two discrete distributions. We've met the binomial and the Poisson. The normal distribution is a continuous curve. Okay, and so let's say, for example, to introduce it, we looked at the heights of males and females in the UK. Okay, so what you would probably be expecting is something that looks like this, where you've got two sets of data. They seem reasonably symmetric. You'd be thinking that there's going to be fewer short people and fewer tall people, okay? And the majority of people will be bunched together in the middle. It's not like a situation where, let's say, we've got lots and lots of people who are around 5 foot, and then not many people in between, and then lots and lots of people at 7 foot, okay? So it's not like a situation where you'd have lots of people at 5 foot, and then there's not very many people, and then there's lots of people at 7 foot, okay? That's not our situation, as we would deem it. So this is more likely to be the case, okay? That we've got most people are bunched into an average height in the middle, okay? So, height in this case, like weight, is a continuous variable. So you can consider this as a continuous random variable that we're working with. So you can apply this to look at the weights of cans of baked beans if you wanted to, or the heights of trees or things like that. What's the probability of, if we've got a normal distribution, of finding a tree that's of a particular tree, like an oak tree, that's taller than, I don't know, 3 meters, for example. Okay, so that is a possible question that you could ask. And it's not just 3 meters. You could go, what's the probability of getting a tree that's like over 3.1 meters or 3.01 meters? It's not the case of Poisson or binomial, where you had to have integer values. So either 0, 1, 2, 3, 4, 5, okay? Now you get 5.2378, okay? So anything in between. So the bell curve that we use is a curve that is centered at the mean, okay? So the way that we draw it is like this, and we'll draw quite a number of them. Mu here is representing the mean, okay? And it's symmetric about that. So it is perfectly symmetric. Now obviously, like if you were thinking about the distribution of heights of males or females in the UK, it's not going to be perfectly symmetric, okay? But you can use a normal distribution to estimate it. Now, although this doesn't really come up that much, effectively the mean, mode and median are all the same for a normal distribution, but we really just can kind of focus in on the mean. Because this is a distribution, as a probability distribution, the area is equal to 1, okay? So the area represents the probabilities. Much as you would think, like when you're adding up all the bars in a binomial Poisson, they add up to 1. Okay? Now, this curve goes on forever in both directions. Okay? This x-axis is an asymptote. Okay, the curve gets closer and closer and closer to it as you get further and further away in both directions. So it's kind of like the further away you get, the less likely something is going to occur. Okay? Yes?
How's the area work? It just keeps going on forever.
Can you remember last year when we looked at sequences and series and we did summing to infinity?
Yes.
Right? So you saw then examples where you can add an infinite number of things together and you get a finite value. That was the whole idea of summing to infinity. So, for example, if that box represents 1 and I draw an identical box next to it, then that's 1 plus a half plus a quarter plus an eighth plus a 16th plus a 32nd plus a 64th, etc., etc., etc. And I'm adding on smaller, smaller, smaller pieces. I'm adding together an infinite number of things, but I just arrive at 2. Okay, so it's perfectly reasonable to then think that this has area 1, although it just goes on forever. Okay, in a similar way. Now, for a normal distribution, it is governed by 2 parameters. Okay, so for binomial there were 2, for Poisson there was 1. For a normal distribution there are 2. And the 2 parameters are, and we say that x is normally distributed, so capital N, with a mean, mu, and variance, sigma squared. Okay, so we have a mean and a variance. Now you've got to be careful. It is the variance there, okay, that's recorded in this notation, not the standard deviation. Okay, so it's the standard deviation squared that's recorded, which is annoying because we use the standard deviation pretty much all the time with normal distribution calculations. So it's a bit of a nuisance that we record the variance. But that's the standard notation that goes with it. Now, because of its symmetry and how it is set up, the majority of the data, and we're talking 99.7%, it's around about that, is within 3 standard deviations of the mean. Okay, so if you looked at going 3 standard deviations down and 3 standard deviations up from the mean, then that would contain approximately 99.7%. Okay, so some people try to remember it as just 99%. Okay, so you can have within 3 standard deviations is approximately 99%. Okay. You know, if we were being accurate about it, it would be 0.9973002037. So 99.7%. Okay. Useful to remember that. So nearly everything lies within 3 standard deviations. Nearly 100%. Okay, not quite obviously because it goes on forever and ever and ever in both other directions. Okay, so this is kind of like the setup. So if you split it up into standard deviations, then the first standard deviation, 1 standard deviation away, is approximately 68%, 2 is 95, and 3 is 99. Okay? So we'll write that down as a bit of information. It's about 95% of the data. That's about 68. Okay? So that's kind of how it's split up. So let's say we go back to the males and females. We've got two normal distributions, okay? So what we're going to do is we're just going to look at seeing how things slightly change, okay, as things are changed. So let's say we've got the female distribution at 163 for the mean and a variance of 252, okay? You don't need to take notes here if you don't want to, okay? It's just so you can like visualize what's going on. The males is 178 and 252, so the only difference is at the means, okay? So if you drew the two distributions side by side, that's what it looked like. Same shaped curve, okay, because the variance just tells you how spread out it is. One's just further along than the other, okay? Now if we changed this situation, okay, so different means. If we change the situation so they had the same mean but different variances, the blue curve here has a larger variance, so is more spread out than the red curve, okay? Notice how it is shorter. Why must it be shorter? You want to think of why it must be shorter. Jane? The area still has to be equal to 1, and so those areas have to represent the same thing, okay? So they're both the same area, it's just this one is kind of further stretched out. So, how are we going to calculate any probabilities then? Okay? This is really the nuts and bolts here, okay? So, what you can be asked to do is to find some areas. So, maybe you're asked to find what's the probability of getting below a certain value, or above a certain value, or between two values, okay? But because all of the problems that we face, you know, if one moment we're looking at the heights of males and females in the UK, and one moment we're looking at trees, the heights of trees, we'll have different means and different standard deviations, okay? But in your formula booklets, only one set of tables. But each of those curves is different. Each of them will have a different height, each of them will have a different shape. So how can we just use one set of tables to work out all of the problems that we consider? Okay? If I had to do this from scratch and just had to work out the probabilities without the tables, without the calculator that can generate these, I would have a very hard time doing this. I have never done this myself, kind of like from scratch, even having done statistical distribution theory at degree level, right? We don't bother. The main problem is that the curve has an equation that looks like this. So 1 over sigma times the square root of 2 pi times e to the minus a half of x minus mu over sigma squared. And if you wanted to find the area, you have to integrate that. And you can't, from the methods that we have, we cannot integrate e to the x squared. That's what the problem would reduce to. So from a calculus perspective, we just cannot do it. Okay? So we'd have to do it numerically, which causes problems. So all three of these situations where we've got different means, different variances, you'll have these different shaped curves. What we're going to do is we're going to put them through a transformation. Yes?
Why can't you integrate to the x squared? Could you do it like similarly to how you integrate log x? Like with doing it by parts?
No, because if I tried to do e to the x squared by parts, the u would have to be 1 if I tried doing it in the log way, and that just reduces to me having to integrate e to the x squared. That's the problem. And I can't use integration by substitution either, because the substitution naturally would be the x squared, u equals x squared, but there's nothing then to cancel out the 2x that I get. So that doesn't work. So what we do is we go through a transformation that stretches and moves all of these different strange shaped normal distributions, okay, ones with different means, one with different variances. We move them and squash them into one standard normal distribution, okay, using a transformation. And the standard normal curve has a mean of 0. Well, we usually write z here. So z is normally distributed with a mean of 0 and a variance of 1. Okay? They all get transformed into this. And the tables use this distribution. Okay? This is the one that the tables refer to. So how do we get from all of those down to this one? Okay? Well, we use this formula here. This is not given to you. Z equals x minus mu over sigma. Okay? So let's say we've got this curve here. We've got a situation where the mean's 100 and the variance is 15 squared. What I would need to do is, if I needed to find a particular x value, I'd have to put it through this transformation. The mean 100, standard deviation is 15. So if I had to look at a particular value, let's say 115, I plug it in, and I get a z is 1. So the 115 in this graph over here mirrors with 1 over this one. Okay? So that's the idea. Right. Are there any questions about this general setup? Or are we ready to see an example of how this works?
Ready.
We ready?
Yes.
Right. Let's do this. So, we've got a normal distribution with a mean of 10 and a variance of 4 squared. And I'm being asked to find the probability that x is less than 12. Okay? Right. Now, what I want you to do with your normal distribution problems is to draw a diagram. So, we get into the habit of drawing a normal distribution curve. Here's the mean at 10. Here's 12. I'm being asked to find this area. Now remember that all of these curves are symmetric, right? So that half is a half. So the answer that I must get is going to be greater than a half, okay? It must be over 0.5. So we put the number 12 through the transformation. We need to find the corresponding z value. So z equals, the x value is 12. That's the one I need to change. Take away the mean, divided by the standard deviation. So 12 take 10, it's 2. Divided by 4 is a half. So that's 0.5. So instead of looking up less than 12, I need to look up less than 0.5. Oh, z. Must write z. Okay. Now we go to the tables. Okay. Right, we are on page 22. Okay? So page 22. Now, on page 22, you will find on the left-hand side, because we're looking at the left-hand side for this, okay, the z values here, okay, downsides. So if we're looking at 0.5, we're looking at, down there, at 0.6915. So what we often write is that this is equivalent to writing phi of 0.5. These mean the same thing. So 0.6915. And that is the probability. So you look at the 0.5 and there, 0.50 effectively.
Wait. How do you know?
So 0.50, 0.51, 0.52, yeah? Well, 0.50, right, it's the same as 0.5, right? Now, over here, right, this extra stuff that you see over the side, if you had to look up, let's say 0.4, let's say 0.498. Let's say you had to look up that, right? Go to 0.4, 0.49, right? And then the 8 is that one. So you add 29 to 6879. So 29 plus 6879 is 6908. So it'd be 0.6908. Okay, reading from the tables. Okay? So that's how they're used. Now, we also need to know how to do this on a calculator, right? Wouldn't it be great if we could just do this on a calculator without the tables? Right. So, I'm going to go through both calculators, because we're going to half and half. Silver first. Right, so if you've got a silver, get your silver out. First of all, need to put it into stat mode. So that's just easily done by going to mode, number 3, and then just pressing AC. Okay, put us into stat mode. Right, then you go shift 1, and you should find number 5 says distra, like distributions. Now there are a few options, P, Q and R. If you're using the silver, you will only ever use P and R. Okay? So 1 is P, 3 is R. This one means less than. This is greater than. Okay? That's what those ones mean. So if you want to do less than 0.5, you do P, so number 1, and then press in 0.5, press equals, and you should get 0.69146. Right? Which is a more accurate version than the tables. Okay? You can either use the tables or you can use your calculator. Your choice. With the Casio Class Whiz. Now the Class Whiz can find you the probability, right, straight off without finding Z. However, do not do that in the exam. You must show working to get there. So you must at least show getting to here. Okay? At least. So, number 7 for distributions. So go into menu, then number 7. You want number 2 for normal CD. You will never use normal PD. Okay? Only ever normal CD. You'll find that there's a lower and an upper. Okay? There's a lower and an upper, right? The lower and upper values are based on what your Z-curve actually looks like, right? So, if you're looking at 0.5, so there's 0, there's 0.5, you want less than it, so this is your upper, right? The lower, remember that the graph, the distribution is 99.7% of it is within 3 standard deviations of the mean. Okay? So as long as you put in a number that's reasonably less than -3 into your lower, so I usually put in -10. Okay, that's what I often put in. So I put in -10 as the lower figure, 0.5 as the upper figure, leave the sigma as 1, the mean as 0, okay, just don't fiddle with those, press equals, and you'll get 0.6914624617, an even more accurate figure than we've had before. Okay, so you've got tables, I would say as backup. This guy, at the very least, P's and R's. This one, normal CD. Okay? Right. Let's say we wanted to find an in-betweener. If we want to find an in-between, if I want to find an in-between, okay, this is the same as just thinking, right, as an area, like if you were doing integration, you could do, well, 1, take away 0.5, right? So you do z less than 1, find that, take away z less than 0.5. In the normal CD, the class width calculator, you'd be able to put in the lower as 0.5 and the upper as 1. Okay? For those of you with the silver calculator, you can do P of 1 and then take away P of 0.5. Or from the tables, you're going to have to find the 2 values and then subtract one from the other. Okay? That are in the table. So there's a few different ways of doing it. Right, so I'd like you to try one, I think, before we progress on. So, okay, could you write down all the working that would go with finding this probability, please? Okay, so the mean 150, variance is 3 squared, and I want to find the probability that x is less than 156. Now, if you were doing a problem where the z value you get is negative, which it can be, because if you try and find any z value that's to the left of your mean, okay, any value that's down here, you'll get a negative value for z, okay? Because remember z, there, the mean is 0, so anything down there is going to be negative. If that's the case, and then you had to find that probability and try to use your tables don't contain any negative values. Okay? So, personally, I would just be saying to myself, use the calculator, right? Because the calculator is not going to worry about it being negative or not. However, if you get to the situation in the exam where you forget how to use your calculator to do this, and then you had to do this as a backup, then what you must remember is that the normal distribution curve is symmetric. So the area that's to the left of -1 is the same as the area to the right of 1. So what you could do is you can look up 1 in your tables, right? That's perfectly fine. And then, once you've looked up less than 1, you've got that. So then you could just subtract it from 1. Okay? So remember, the whole thing's 1. If I find the area to the left, I can just subtract that from 1. That gets me that area there, which is the same as that one. So as long as you remember your symmetry of the curve, you can use the tables to do that. Right, here's something for you to try. Find me each of these probabilities. Okay? Now, some people have been questioning number 6 as to why that would be the case, or how do you do it. You could put it through the formula if you really wanted to, okay? Put it through the z equals formula, but the idea really is you're trying to find an area of a line. Okay, so for a particular value on your curve, the area will be 0, okay? If you want it, it's kind of like, well, why would that be the case? It would be something like if, let's say this represented, oh, I don't know, it doesn't have to be that number. It could be something like the males in the UK, what's the probability of picking up somebody who is precisely 6 foot tall? To the atom. Okay? And then you're kind of really thinking, well, that's very unlikely to happen, right? In fact, it's 0. Because there's an infinite number of possibilities in between, and picking out 1 out of an infinite number of possibilities is 0. Okay? So, really, that's why number 6 will be 0. So if you could, you know, you might think of it, oh, that's a bit of a trick question, but, you know, there's no reason why that kind of question can't be asked. And likewise, if it's not equal to 57, then, well, it's 1. Or not equal to 56 would be 1. Not equal to 100 would be 1. Okay? So, these are finding basic probabilities from the normal distribution curve. We're slowly building up our skills of being able to do that on the calculator to help out. So, what we're going to finish off with from the MEI S2 book, page 44, question 1 to 4 and question 6, okay? So to give you a little bit of extra practice.